Today we have Ole Jensen speaking. He's coming from London. He started his undergrad and masters at the Technical University of Denmark, and then he moved to Brandeis, where he worked on short-term memory models with John Littman before doing a postdoc at the Technical University of Helsinki, where he started doing his MEG work. And in 2002, he moved to Dundas and has been there since, where he's now faculty at the Dundas Center. So welcome.
Yeah, thanks very much for having me here. So what I'm going to talk about today is functional architecture and how that can be set up by oscillatory activity. And it's something we currently are quite excited about because we have some findings that really help us to bring new insight to this question, we believe. So as you probably all are aware, the brain is a very complex organ, and it has to process information coming in on a somewhat fast time scale, but the brain also has to work very dynamically in order to process different kind of informations and switch tasks and so forth. And that is, of course, if you want to study the brain as a network, we also need to understand how that is achieved. So basically, we would like to characterize the activity in the different nodes of the network of the brain, and then investigate how communication between these nodes are done. And when it comes to functional MRI, some progress has been made there, right? With PPI analysis, DCM, and so forth. However, with functional MRI, as you know, one measures changes in blood flow, so there are limits to how fast changes we can look at. Then one would think when using whole head EEG or MEG, we should have the sort of unique possibility to study these fast dynamical processes related to how the network works. However, I would dare to say that we have not been that successful in studying the brain as a network by electrophysiological means. And why is that? Well, I think part of the story is that we don't really have a good sort of theoretical framework or notion for how to study this. So, of course, when we think about a given process engaging various regions, then you could assume that in order to understand this, we have to understand how this region hooks up and talk with that region and talk with that region, right? But as it turns out that many of these regions are already connected, so how they are hooked up is actually not so important. What might be more important is to understand how regions not involved in doing a given task are being disengaged or inhibited, right? And you can even take the extreme view that functional architecture is not about connecting the right regions, it's simply about inhibiting task-relevant regions. And by doing so, you leave the relevant regions to do the processing. So how can we get closer to studying that? Well, now it is so lucky that I think there's more and more evidence for oscillatory activity in different frequency bands are reflecting respectively processing and inhibition, right? So you're probably all aware about the findings demonstrating that gamma activity seems to have something to do with neuronal processing, right? And indeed, one can study gamma activity in different networks and explore how that might be involved in setting up the processing stream and neuronal computation. And I guess a week ago, Ingrid Nieuwenhuis was here, PhD student of mine, showing some work on how gamma band activity and correlation between power in different regions reflect communication between these regions in the context of a consolidation study. When it comes to the inhibition or disengagement, which I'm going to focus on, well, then it turns out that we are now pretty certain that alpha and maybe also beta reflects functional inhibition. And I'm going to make that case. And that is now going to be quite important because by many, alpha is sort of considered the boring rhythm, right? It has sort of been very underappreciated. and to some is actually considered noise. If for people doing ERP studies, you will often hear that subjects with strong alpha are problematic because this alpha activity provides or just serve as noise variance when doing the evoked responses. And you also see people doing the recordings, the EEG recordings, when alpha start to grow, they start cursing, right? And they stop the experiment, give the subject a coffee. But what I'm going to claim here is that alpha is essential. It's not just something sitting there in the background being a nuisance. It's actually essential for optimal brain processing. And if I'm right about that, of course, we sort of have to rethink how we look into electrophysiological signals. So this is sort of going to be the game plan here. I'm going to make the case that alpha reflects functional inhibition, gamma reflects processing, and then I'll address how communication between different regions can be studied by looking at cross-frequency couplings between these alpha-beta and gamma-theta rhythms. And furthermore, I'll end with a story about how modulations in alpha activity actually can create event-related potentials and fields. Because, of course, it's not very satisfactory that we have one group of people doing ERPs and EIFs and another group of people looking at oscillations. There might be a connection between these two phenomena, and we have actually identified such a connection. But first, to get to it. So what brought me into alpha initially was a working memory study. But first of all, I should say that alpha has been around since the late 1920s. It is the strongest signal that we can measure from the brain. Here's just an example of ongoing alpha activity. It is these oscillations that you very clearly can see with the naked eye, right? And they have to be produced by huge groups of neurons oscillating in synchrony. So it's a well-known phenomena, very old, but it also turns out that alpha is modulated by various cognitive tasks. And what really brought me into this was a study on working memory. And years back, we developed, together with John Lisman, these models for how theta and gamma oscillations were supposedly involved in working memory maintenance. So we did the following study where we presented items 2, 4, 6, and then there was a probe coming up. Subjects had to say yes or no to whether the probe was in a list. So just a basic Sternberg study. And what we then looked at was the retention interval and basically calculate the power spectra and ask, was there modulation with load, right? What we found was that the strongest activity during the retention interval was in the alpha band, right? So this is a power spectrum, this is 10 hertz, so we see strong alpha during retention. So the sort of old notion that alpha reflects idling and pops up when you're drowsy or when you don't really do processing does not really hold water, right? We see strong alpha activity during the retention interval where you have to concentrate on keeping these up to 6 items in memory. But the real surprise was when we looked at the modulation in alpha with respect to working memory load. What we then see was that alpha is increasing systematically below 2, 4, and 6, right? So the more you keep on working memory, the stronger the alpha. Then you might argue, well, alpha is involved in some sort of mechanism juggling the different memory items. And the more items you have riding on alpha, the stronger the alpha rhythm. That's one possibility. But we actually were not so happy about that view. So we thought about maybe alpha is reflecting functional inhibition, right? So the notion would be that the more we have to keep in working memory, the stronger the alpha rhythm inhibiting posterior regions in order to reduce visual input that might interfere with the working memory maintenance. In other words, alpha has something to do with resource allocation, right? So to allocate resources to frontal regions, maintaining the working memory items, you are shutting down sensory information, and that is exactly what alpha is doing, right? So to substantiate that notion, because I mean now from these data we cannot tell whether alpha actually is doing this inhibition or whether it is reflecting the working memory maintenance per se, right? in order to get into this, well, we devised an experiment in which subject had to keep in working memory a phase identity. So they are shown a phase and later on a probe phase, and they have to ask whether this phase matches the first phase, right? So we also had a different task in which subjects were asked to remember the phase orientation. So exactly the same phases were presented, but a probe comes up indicating whether the phase is looking to the left or the right. So we did this, of course, because we wanted to engage either the dorsal or the ventral stream, right? So supposedly in the phase identity task, the ventral stream is being engaged. In the phase orientation task, the dorsal stream is being engaged. And that was our basic manipulation. And the results of this came out quite clear, in a sense that when we have the phase identity task engaging the ventral stream and look at activity recorded with MEG over the dorsal stream, well, what you then see is that there is strong 10 Hz activity, right? So this here is a time frequency representation. Time frequency power calculated for the individual trials. The red here indicates strong alpha activity. Here 10 Hz, right? I forgot to mention, I don't know if all of you are familiar with MEG. For now, think about it as EEG. It's just we have a better spatial resolution, so we have a better ability to localize the sources. But fundamentally, there's no major differences. It's basically electrophysiological signals they pick up outside the head. Okay, so strong alpha activity during the phase identity task, and in the phase orientation task engaging the dorsal stream, we see little alpha activity, right? So this pretty much makes the case that when you engage the dorsal stream, alpha is low. When you engage the ventral stream, alpha is high, supposedly suppressing processing in a dorsal stream, allocating resources to the ventral stream. So to us, this really makes the case that alpha is not memory maintenance per se, it is functional inhibition. Yeah?
Was the alpha over the ventral, in the ventral electrodes changed significantly?
We would have hoped to see that, but we did not. So I can get back to this later, maybe a discussion about how general these phenomena is. But basically, we don't see the ventral gamma, and we do not know whether that's because the ventral stream is sort of further away from the sensors, so there's a small signal, or whether it's not there. And I think we need to look at intracranial data. I mentioned we are using MEG. That means that we can localize the sources with a fairly well accuracy. So if you look at the example here, it's this posterior alpha modulated with the task, and we see the alpha to be around parietal occipital areas, maybe sort of bleeding down to occipital regions. So that means this is like the good old alpha, right? It's the alpha that also Berger reported over the posterior regions. It's the alpha being modulated by eyes open, eyes closed. So no big surprises here, basically. Good. So this really, at least to me, helped to substantiate the case that alpha has something to do with functional inhibition. Then to the gamma band. We also looked at gamma band activity in the very same task. And I should say our motivation for looking at gamma activity is twofold. One point is that we are also embracing this notion that gamma has something to do with representations in the light of the binding hypothesis, right? So you're probably all familiar with this notion developed or say promoted from the Singer lab, that if you have this picture here, you have a woman and a cat. There's some neurons coding for the woman, some for the cat, and in order to form a percept of the cat, this neurons coding for the cat oscillate or firing together. They synchronize their activity. Not only that synchronization is dominated by the gamma frequency rhythm, but the synchronization would not be in phase with the neurons coding for the woman. So if you don't fully embrace this binding by synchronization, then at least you might still accept that, well, gamma activity has something to do with neuronal representations. That's argument one. Argument two is that, well, if you have neurons in a network and they synchronize, well, then they're going to shout really loud, right? They're going to project very strongly to downstream regions. So if nothing else, synchronization in the gamma band is important because these neurons are going to be hurt by other networks. And what we here specifically hypothesized is that in a working memory task, if you have neurons coding for a phase, say, then they fire together, they represent the phase, there's the retention interval when the phase turns off, well, then the memory trace is being carried by the synchronization being sustained, right? So not only does this provide sort of a hypothesis for how the trace is being maintained, but it also means that we should see fingerprints of working memory maintenance in representational areas. And we now take the very same task and we go to the higher frequencies, the gamma band. And again, it came out very clear, our findings, in the phase identity task engaging the dorsal stream, we see low gamma activity. Phase identity engaging the ventral stream, we see low gamma over the dorsal stream. However, over the dorsal stream, we see high gamma activity, right, for the phase orientation task, right? So in the stream being engaged in the working memory maintenance, we see the increase in gamma. Again, same concern as you raised up. We unfortunately do not see the gamma in the ventral stream. Then you might say, hey, wait a minute. We also know that gamma is related to attention, maybe even vigilance. So could it be so that this gamma activity here is just a simple correlate of vigilance or attention? And it turns out that that cannot be the case because we happen to be so lucky that the phase identity task was the most difficult condition, right? Yeah?
You could, another phrasing of this critique would be spatial attention versus feature attention, right?
Yeah,
but then the RT
but that I'm fine about because I would say if you think, yeah, and if you think about working memory maintenance is sort of internally paying attention to a representation, then you can think about that as being the mechanism for working memory maintenance. What I'm more worried about is sort of general vigilance changes. And then it turns out that it is actually in the most difficult task where we see less gamma activity, right? So at least we can rule that out. And that is in comparison to other working memory tasks where one compares control stimuli to actually the working memory task, which typically is more difficult than the control task. Here we are so lucky that if you think about the phase identity task as the control task, the gamma is actually less. I think you had a comment?
Yeah, well, when you go back a few slides where you showed the alpha activity, you also had in that site, which was
okay, this
a
here.
vital site, you actually had increased gamma when you had increased alpha. There, right? Go back one.
Yeah,
so
this is a bit slow.
It's kind of complicated. So like, I mean, in up to 30 hertz, you have, if you, maybe that's not statistically significant, but
Oh, this here.
Yeah.
Yeah.
I mean, usually I'm thinking when you have more alpha, you have less gamma.
Yeah.
And
But that also holds up here, unless you consider this gamma.
right.
Yeah. So what goes on here could be several things. It could also be a harmonics of the alpha rhythm, but basically it wasn't terribly. It wasn't significant what occurred up here. So the strongest modulations are in the alpha and gamma band. But I should also say that the gamma band sort of shifts up every year, and shifts up in frequency.
Oh, okay. Yeah.
But at least these days, it's in the 60 to 90 hertz where we see the strongest modulation, in the cognitive modulation in the gamma band.
Well, it just is a slightly more complicated story because it depends on the site of the electrode. And I have no question about your great interaction with a difficult task, showing less gamma. I mean, it's all very interesting in a more lower site.
Yeah. Yeah, I'll show you an example with even higher gamma. So your argument about where you look is, I buy into that, yeah. we can also localize the sources for this gamma activity, and basically it goes to occipital regions. That being said, this here looks a bit spotty, right? But that's with MEG source modeling is never perfect, and our signal to noise for gamma is not so great, but at least I'm fairly confident that it is quite posterior in occipital cortex. We see this gamma activity, so in the representational areas.
What about
the cerebellum? Yeah. Personally, I don't believe it. So, I mean, you have to take source modeling with a grain of salt, right? So basically, we are somewhat... Yeah, I mean, so we like to be somewhat conservative in the sense that we say we see something at the sensor level, we have the strongest effect over the back of the head. Now we ask where these sources most likely to be. Well, in occipital regions. Possibly it's in the cerebellum, but we don't have a lot of confidence in that due to the noisiness of the source estimate.
What kind of source estimate do you use?
We use a beamforming technique, so it's a spatial filter approach. Yeah. Good. So hopefully I've now made the case that in this task, gamma seems to reflect functional disengagement, and alpha reflects functional inhibition or disengagement, and gamma reflects the processing, right? But I would like to go even further and then say that alpha is not just sort of a side phenomena of a region not being engaged. I would like to make the claim that the inhibition by alpha is required for optimal task performance, right? And to do that, I will show you some data from a recent working memory study in which subjects had to remember stimuli with a given frequency presented electrically to the median nerve. So you can think this is about this as a somatosensory working memory task. And they simply had to ask whether the second pattern here was higher or lower in frequency compared to the first pattern, right? And it should also be mentioned that the stimuli for the sample was presented only to the right hand. So we can then look in the contralateral somatosensory regions. And the findings here came out quite clear, in a sense that we made the task sufficiently different such that subject made quite a few errors. And then we could compare successful versus unsuccessful or hit versus miss trials, right? And then we simply looked at the alpha activity, comparing those. And over a broad region of sensors, what we saw was more alpha activity for hits than for misses. And when we look at the sources of this, we see the alpha activity in occipital regions, but also in right hemisphere, sensorimotor, and extended regions, right? So in the hemisphere, not being engaged in the task, we see stronger alpha, and this alpha is actually stronger when people do the task correct, right? So to me, that helped us to really substantiate this case that the alpha activity is a necessity for people doing this task properly. And the interesting thing is that we also looked in the gamma band, and when doing so, we now see this very broadband gamma activity, but we find it in bilateral regions, and we can localize it to what we think is secondary somatosensory regions. However, when we compare hits versus misses for this gamma band activity, we do not see a difference, right? So it means that the performance of the task is more dependent on subjects' ability to disengage irrelevant regions than to engage relevant regions. Okay, moving onwards. So hopefully I've now made the case about alpha and gamma activity. Now I would like to move on to a network consideration, right? So of course, to understand the full network, we need to understand how these oscillations in these different regions are interacting. And you are probably aware that one of the ways that people have been looking at networks using EEG and MEG data is to use coherence, right? Phase synchronization in different frequency bands between different regions. So I might offend someone by saying this, but at least to my reading, there's not that much being reproduced doing that, right? The idea was already published in the mid-70s in a science paper looking at coherence, and that should reflect communication between different networks. It might be a true phenomena, but my claim here is that we have not really been able to detect this using EEG and MEG, basically because nothing has been reproduced. So we need to open our mind to look into different ways of correlatedness. While we should not give up on coherence, I'm just arguing we should also look at other ways of interactions. And of course, the theta gamma cross-frequency interactions done here by Canolti and Knight is one approach. What we have been playing around with is power-power correlations, right? So in other words, we would also expect now that in a given task that what is going on in one frequency band in a disengaging region and in a frequency band in an engaging region should be correlated. So I'm going to show you an example for how to study these sort of things. And what we have been employing here is a simple go, no-go paradigm. So subjects get a string of digits, and they have to press to every digit, but they have to hold back button presses to number 5, right? So basically now and then, since they are pressed for time, they make a mistake. What we then can do is first to go in and ask, is there something about the brain activity before they make a mistake, which is different compared to when they do not make a mistake, right? So basically we are going to look at pre-stimulus activity. And what we found quite clearly was that, well, if there is stronger alpha activity in posterior and sensory motor regions, if there's strong alpha activity, people are more prone to make an error, right? Whereas the alpha activity, if it's not so strong, people are more prone to do a correct response, right? So the pre-stimulus activity in alpha band is predictive of subsequent performance. Yeah?
Just look at the exact phase of the alpha.
Yeah, and we would have loved to see a phase relationship, but we were not able to find that. But I should say there's just a paper out in Neuroscience by Matthewson in a visual detection task, and they find that pre-stimulus alpha phase also is a predictive of subsequent processing. So just as a side note, when we're talking about oscillatory activity and functional architecture, then I'm not only talking about functional architecture when a task is being performed, but also that this functional architecture might be set up prior to the stimuli coming in. And that is exactly what you might be seeing here. Okay, so what happens after people have made an error, right? So basically now we can compare button presses with respect to erroneous presses and correct presses, right? And what we see over frontal regions is a lot of activity in the theta band. And this here might reflect the frequency representations of the good old ERN, the error-related negativity, right? So more theta or frontal regions, quite broadband, reflecting errors. What we see over the back of the head is more alpha depression, right? So if you make an error, alpha goes down or posterior regions. So when we saw this, then we were like, we were thinking like, hey, could it be such that when you make an error, of course you are trying to avoid an error in the next trial, so maybe you set your functional architecture of the network such that you are less prone to make that error, and we know that alpha reflects errors, so the name of the game here would be to reduce the posterior alpha activity. So in order to look into this, we simply correlated the posterior theta activity, the anterior theta activity with the posterior alpha activity on a trial-by-trial basis. And what you see here came out very clearly, right? So basically we pick, in this case, 2 frontal sensors, we look at the theta activity, and then in the same trials we look at the alpha activity in all the other sensors, and then we simply do a correlation between the frontal alpha and the theta activity in all the other sensors. And we do that for errors versus corrects, right? And what we then see is that there's a strong correlation between frontal theta and posterior alpha, or an anti-correlation actually, right? But for the hits, we do not see that. So in other words, to us, this really speaks to the interpretation that after an error, we have this frontal theta activity that then results in a posterior alpha depression, making the system less prone to commit errors. So this here is also an example of functional connectivity, if you will, or a study of the functional architecture of the network. Yeah?
It was the case that in the subsequent no-goes that the performance was better.
Once again?
Was it the case that in the they make an error and then you're saying to avoid errors subsequently?
Yeah.
You expect an improvement in their performance following errors.
Yeah. Yeah, so basically after you have made an error, you are less prone to make an error in the next trial. Yeah. And yeah. Good. So hopefully now I've also brought about a case. We have other cases as well, but here at least we have one concrete case where we can study the network of the human brain by looking at power correlations over trials. Okay, so actually how much time do we have?
1 o'clock.
Hmm?
Until 1 o'clock.
Until 1 o'clock. Okay, so I will just zoom through this. This.
We can go over a bit.
Okay, so but I'll just zoom through this here somewhat fast because you're probably familiar with the analysis and so forth. Because what we then looked at next was the interaction between alpha and gamma activity. And what we applied was a method very similar to what Ryan Canolta did by looking how the phase of slow oscillations, in this case alpha, is modulating the power of a faster rhythm in the gamma band, right? And we have here a plot where you see the slow oscillations and here the power of the faster rhythm. And what we basically see is that the 10 Hz activity is modulating activity in a band from, say, 30 to 70 Hz, right? So there's this coupling between the alpha and the gamma activity. There's also some subtleties with respect to the phase, but I'll not get into that. Yeah?
So it's maybe a stupid question, but why don't we say alpha the other way around? Like high gamma modulates alpha. What's the causality here?
That's possible. Yeah.
Is there some functional arguments why it's low frequencies modulated high rather than vice versa?
I guess not. I guess one could maintain that argument, but I'm not sure it's going to change. No, I mean, I'll say what I think about it, and then maybe we can address your question again. Because basically what we see is that gamma activity, at least we think, is modulated by the slow alpha activity.
But that's just an observation.
That's an observation, yeah. Yeah.
The alpha activity changes with the alpha frequency.
Yeah. So that.
He's just reporting that observation.
Yeah.
The title says alpha phase modulates gamma.
Yeah. So strictly speaking, I'm not allowed to. I should make this statement. That's correct. Yeah. No, I mean, you're correct. I mean, I can, strictly speaking, I cannot infer causality here, but I'll tell you how we interpret this. And the way we interpret this is that, because now we say there's something funky here, right? Because before I said alpha reflect processing and alpha gamma reflex processing and alpha reflex inhibition. But now I say they are somewhat correlated, alpha and gamma. So what's going on here, right? So actually the way we think about it is that you have ongoing gamma activity, and now you have the alpha rhythm coming in, and it's going in and it breaks the gamma activity, right? So you can think about pulsed inhibition, right? And then the stronger the gamma activity. So here you have the ongoing gamma activity, and alpha comes in and break the gamma activity, and the stronger the alpha activity, the shorter windows of processing you have for gamma, right? So you can think about sort of a graded phenomenon in which you can shut down a region more or less by increasing the magnitude of the alpha activity. Furthermore, that also leads to sort of a rethinking about alpha, right? In the sense that now I mentioned pulsed inhibition. That is different from talking about something oscillatory where you have something positive and negative. Here I'm talking about sort of bouts of inhibition. And that's going to bring me to the next issue about how oscillations, they relate to event-related fields. But just to summarize this part, we have the alpha doing the inhibition, we have the gamma doing the processing, but it's not a binary thing necessarily. You can think about sort of a graded inhibition by alpha, so you allow the system to do some sort of processing in a gamma band, but it can be more or less blocked by phasic inhibition by alpha. Good. Next is event-related responses. So here I just put up a lot of different examples of event-related responses being studied in cognitive neuroscience, right? Now, it's not very satisfactory that there's guys like me promoting oscillations, and then other guys out there promoting event-related responses, albeit we are working on the very same data, right? Is there a connection between oscillatory activity and evoked responses? So that is the key question here. But first, one observation. It turns out that many of these event-related responses that we measure in cognitive neuroscience have a very slow time course. There's the focal study where you see this systematic increase in event-related responses with working memory load. There's the long-term memory findings, some subsequent memory and recall. There's the movement preparation potentials, the Bereitschaft potential, also having a very strong, it builds up over a second. In language research, there's these, for instance, the P600, also a very slow component. Right? So if you now start to think about this from a physiological point of view, it actually becomes quite mysterious, these slow fields and potentials. Like, how are they produced? I think everybody would agree that evoked potentials have something to do with synaptic activity. But in order then to get a sustained evoked response, you have to imagine sort of a constant bombardment of synaptic input, but this bombardment has to be asynchronous. It's not impossible, but it's somewhat awkward in relationship to how we think about the early evoked responses, which is really due to synaptic input being synchronized due to stimuli coming from the outside, right? So this is true synchronization, and this here has to be desynchronization of synaptic activity. Yet these sustained fields here is as big in magnitude or maybe even bigger than the synchronized activity. There's something weird going on here, right? So we think we might have been able to provide insight into this mystery by a rethinking of oscillatory activity. So this is usually how we think about oscillations, right? Wiggles like this. If you think about alpha activity, these 10 hertz, this would be 10 hertz, and this would be 100 millisecond one cycle, right? Our claim now is that don't think about oscillations like that. Think about oscillations as having this amplitude asymmetry. So peaks are more modulated than the troughs, right? So this is our claim. If you now think about this from a physiological perspective, this is actually easier to envision in a sense that if you think about the oscillations up here, and we know that these oscillations are produced by dendritic currents, well then first you need currents running in one direction, 50 milliseconds later about the same current running in the other direction. It's not impossible, but it's difficult to envision. It's a lot easier to envision that you have bouts of dendritic activity every 100 milliseconds that then is producing your fields here. And then the magnitude of these bouts can be greater or larger, and then you get this amplitude asymmetry. I should also point out that there's nothing mysterious about this amplitude asymmetry, right? So imagine a guy playing a drum. He can hit it harder or not so hard, right? So the magnitude of the booms is modulated, but quiet is quiet, right? So you get asymmetric oscillations. You can imagine you're bouncing a basketball, right? It can go higher or lower, but the floor is the floor. If you measure the light in your office, you have sunny days and not so sunny days, but dark is dark, right? So also asymmetric oscillations. So it turns out like no matter where you look, asymmetric oscillations might actually be more the rule than the exception. So that now introduces a serious problem and then later a solution. But first there's a problem for how we look at ERPs and ERFs, right? Because the basic notion over the last 3-4 decades has been that oscillations wash out by trial averaging. But as you will see here, that the mean of this signal is biased by the magnitude of the signal. In other words, these oscillations here would not necessarily wash out, right? And to make that crystal clear, I will show you how we first typically think about oscillations, right? The symmetric ones. We have ongoing alpha oscillations. There's a stimulus coming in. They're being depressed. This is what you see. There might be an evoked response. Then you might say, hey, wait a minute, this evoked response is very little compared to the oscillations. That's not fair. Not true. It turns out that these alpha oscillations are at least 10 times the order in magnitude of the evoked responses. This is somewhat realistic. First trial. Second trial, the phase of alpha is of course different. Now we add the whole thing up and we get our evoked response. All is fine, right? So now we come to the rethinking of alpha. So all what it means is that we have ongoing oscillations. They are being depressed. Only peaks but not troughs. You get the evoked response. Trial 1, trial 2, trial 3, and so forth. And now we average it all together. So you get an early evoked response and you get a slow component as a consequence of this amplitude asymmetry, right? So here you have a clear-cut example about showing that oscillations do not wash out by trial averaging if they have amplitude asymmetry. Even more, you can create these slow evoked components as a consequence of the amplitude asymmetry, right? So I hope you all follow this because this is really essential for the story. Right? So it's a very simple mechanism with quite surprising consequences. So this is just speculation so far, right? So is this actually a true phenomenon? So to assess that, first of all, we developed a measure. So this is just a simulation. But basically, we looked at the ongoing alpha oscillations, we looked at troughs, we looked at peaks. And we did that by taking this ongoing signal and then we bandpass filtered it. And then we can go back and identify troughs and peaks. And then we have a measure where we look at the variance of the peaks versus the variance of the troughs. Right? So now we can subtract the variance of the peaks minus the variance of the troughs and we normalize that. So we get a number between -1 and +1. And that number is going to tell us about the amplitude asymmetry. Right? So +1, strong amplitude asymmetry. Why -1? Well, imagine this here is flipped down, right? Just mirrored down. Well, then you have the peaks being not modulated, but the troughs being modulated, and that's when you get -1, right? So we implemented this measure, and then we just applied it on some ongoing data. Just eyes closed data from a subject sitting there doing nothing. Strong power, this is a 10 hertz over the back of the head. Now if we apply this alpha index, as we call it, what we see over the back of the head, there's a red blob and a blue blob. We can get into the polarity of this later, but this is fully explained, right? But nevertheless, we do get strong amplitude asymmetry over the back of the head, right? And this is in the 10 hertz band. Furthermore, we can also look at the spectrum of the amplitude asymmetry, right? So we just apply it for different frequencies and plot the result. What you find around 10 hertz, there's strong amplitude asymmetry, and maybe also something going on in a beta band. So in other words, amplitude asymmetry seems to be a true phenomenon, right? Next question, does it then have consequences for how event-related fields are being generated? And okay, so we have a Neuroscience paper where we make this proof of principle for the amplitude asymmetry, but we also demonstrate that it can create artificial, if you will, slow event-related fields just in a checkerboard stimuli task. But what we really want to get at is cognitively modulated event-related fields and potentials. So, to do that, we have been looking into a working memory task. But before I get to that, I'll just explain you the focal study in which sustained event-related fields are being observed, right? So what Fogel did simply was to have a visual working memory task, items presented to the left or the right, a cue tell them where to attend to, there's a retention interval, and then they have to match these items in a test array to the memory array, right? So they have to allocate resources to the left or the right hemifield and sustain those representations. And what he then did was to look at the event-related potentials over the back of the head, and he looked at right versus left sensors. And what he found was these sustained potentials, which was quite different in left and right sensors. And I should mention that these here, they flipped around when subjects were asked to attend to the right. And what he then could do was to subtract right minus left sensors. And in this case, when attending to the left, and he found these sustained fields that also was modulated by working memory load, right? So here's a good example of sustained event-related fields. And this is exactly what we would like to sink our teeth into and just to ask whether this can be explained by alpha oscillation modulations, this phenomenon of lateralized sustained event-related fields or potentials. So to do that, we had some data in a draw from a delayed saccade task. So subjects simply see a dot to the left or the right. There's a retention interval, and then they have to saccade to the dot. So you can consider this here as a very primitive version of the focal experiment with load 1, right? And what we already knew when using this task was that posterior alpha activity is strongly lateralized. So if you focus in front of you, as stimuli come up to the left, you see the right hemisphere alpha being depressed and your left hemisphere alpha increasing. Side remark, this is also substantiating the case that alpha becomes strong in task relevant regions, right? But nevertheless, we see this very strong alpha lateralization. We can characterize that by our time frequency representations. So when the stimulus come on, we see alpha building up. We look at the topography with respect to left and right stimuli, and we get this here over the back of the head. Very clear. We can also localize this alpha lateralization to parietal occipital regions. Good. What about the event-related fields? Well, if you now here consider left channels, you see a sustained field with respect to left stimuli and right stimuli. And that effect here in the sustained event-related fields is swapped around over the other hemisphere, right? So that is exactly what Fogel also showed. Now we look at the topography is over the back of the head, where we also got the alpha modulation, right? So the plot is thickening. Basically, what we're going to do now is to compare this lateralization in the event-related fields. In this case, we look at left minus right stimulation, and we look at the alpha modulation, right? And first of all, you can note the topography is surprisingly similar. What we also did was to apply our measure of amplitude asymmetry to this posterior alpha activity, and what you see is quite a strong amplitude asymmetry in a 10 Hz band. So these oscillations do have amplitude asymmetry. So all the ingredients are there, and now we can start to correlate, right? So basically, if you now correlate the alpha lateralization with the event-related field lateralization over subjects, we see a very strong correlation, right? So typically cognitive neuroscience is not this good, right? But we get a surprisingly strong correlation between the field lateralization and the alpha power lateralization. And this correlation is the strongest over the back of the head. I should also say we correlated the amplitude asymmetry index and the event-related fields. We've also again found a significant correlation, not as impressive as before, but it's still there, right? So how does all this work? Well, basically, this is what we think is going on. Consider that you are recording from a left sensor. Now we present a left stimuli. There's alpha activity. It's somewhat depressed. Now we present a right hemifield stimuli, and then alpha is becoming more depressed, right? We do this over multiple trials. We add it all up. We get an event-related field with respect to left and right stimuli due to the asymmetric amplitude modulation. There's a systematic difference in these slow event-related fields, and that is what turns out as the lateralized event-related fields. So I think here we have a clear-cut case of a cognitive event-related field that can be produced by modulations in oscillatory activity. So does this mean that Vogel should be very nervous now? I don't think so, because what we now have done is to provide a physiological mechanism for the effect that he reported, right? It also means that we know what these event-related fields and potentials actually mean. We know more about that from a functional point of view, because since I've made the claim that alpha reflects functional inhibition, then we also know that these sustained related fields, these sustained fields and potentials have something to do with functional inhibition, right? So they do not reflect the working memory maintenance per se, but they reflect more the disengagement of task-relevant regions. And I think that is also consistent with one of Vogel's recent papers, where he showed that in an attention task, not a lateralized attention task, not requiring working memory maintenance, you see exactly the same sustained event-related fields, right? So just to say, by having this theory for how these event-related fields are being generated, it does not mean that we are going to dismantle the field of ERPs and EIFs. It means that we are going to strengthen it by providing a physiological account for how these event-related evoked responses are being produced. And it allows us to a larger extent to infer what their functional meaning are. So I think I'm going to end here by summarizing alpha, like when information is flowing through the brain.
Before you get
Yeah.
there, can I ask you, so if you're correct, I think it means that if you now add up in a typical experiment, ERP experiment, if you add up instead of just averaging them, if you shift them around, so you average them so the alpha is in phase,
Yeah,
which requires you should be able to do that.
yeah.
Then you should actually see the alpha modulated, if you're right. And if you're wrong, you should see the baseline shift.
Yeah.
Is that was my...
I think that we haven't tried to do that, but I think you're right. So basically, if just after the stimulus we are shifting the individual trials to phase align, we should see alpha with the amplitude asymmetry property rather than a baseline shift. Good one. We should try that. Yeah. Okay. So to summarize, I think when we are going to when we study the brain as a network, it's very important to look into oscillations. Why? Well, because they are modulated by cognitive tasks and they have strong signal-to-noise ratio. And what we would like to understand is how information is zooming through the brain between different networks. But to understand that, maybe the focus should not so much be on how this region talks to that region, maybe the focus should rather be on how we shut up the task-relevant regions, and by doing so, you automatically set up the stream of information flow. Alpha seems to provide the functional inhibition, and that then provides insight into this sort of apparent mystery that has been around for 80 years, like how come alpha is so strong? And in particular, it also provides a functional meaning to alpha, namely that the presence of alpha, I would claim, is essential for optimal task performance. And you might even to take it further and go in and ask in different kind of disorders, such as ADHD, maybe some of these problems about attentional deficit could be explained by the inability to have enough alpha in the correct regions, so to speak. Furthermore, gamma seems to reflect processing, but there's an intimate relationship between alpha and gamma, and you can think about alpha providing pulse inhibition that breaks the gamma activity. This is still a hypothesis, but nevertheless, that's how we like to think about it. So you sort of have a graded inhibition of the processing gamma activity by the alpha activity. Furthermore, modulations in the alpha band can create systematic event-related fields and potentials. This we have only looked into with respect to the alpha band, but it might generalize to other frequency bands such as the beta and gamma band, right? Because, I mean, why should it not hold for other frequency bands? But there's still an empirical issue. So at least something I would like to bring forward to the computational modelers here in this crowd is that I think with all this, alpha is really gaining in importance, and it's really a shame that we do not have a better idea of how alpha is produced by the physiology of the networks, right? There are some models out there, but they certainly could be improved. There's a lot of open questions also on how this alpha activity is being controlled. Is it due to a top-down drive, or maybe is it some sort of lateral inhibition such that if you engage this node, this other node here is being forced into an alpha mode. So this is all what we need to look into in the future, and I really think computational modeling would be very useful in trying to address these questions, combined with more intracranial physiological recordings, both in humans and in animals. So I think I will end on that note. Thank you. Oh yeah, yeah, sure.
So I think there's a really good reason to actually replicate or get Vogel's data, because his working memory task seems to me different than your working memory task, and you might get different results. So for example, his working memory task might be heavily dependent on a visual representation.
Yeah.
Whereas yours, there's a Sternberg task, and then, I don't know what kind of representation this is. But just as in addition to the modeling that you might do with it at the end, the results might flip around, just because it's a different kind of working memory task.
Yeah.
Just as a data point.
Yeah. Sure, that would be good to do this, but because so far we have not demonstrated either this increase in sustained fields with load, because that should also be reflected in increase in alpha lateralization.
Right.
So in fairness to Vogel, to really claim that we have a mechanism for his ERPs, we need to do that. That's correct.
Well, and it just might be a different kind of memory. It might be a different kind of task. You still might be able to model it on the basis of frequencies, on the basis of a time frequency analysis.
Yeah.
But, it's interesting. It would be interesting.
Yeah.
Can you expand on how the asymmetric index of oscillatory activity, or how is the asymmetric representation of oscillatory activity different than looking at the analytic amplitude or the envelope of an oscillatory activity? But because you may think that it's when you generate the spectrogram, what you actually looking at is what is the power in a certain frequency band, or what is the envelope of the power in this frequency band. and it is asymmetric in its nature as well, because the power cannot go below 0 and so on and so forth.
Yeah. So it turns out that if you have sort of an asymmetric oscillation like the 10 hertz, and say you modulate that at 1 hertz, you're going to get a 1 hertz peak in your power spectrum as well.
Right.
However, had you had symmetric modulations, you would not get a 1 hertz peak, you would get a 10 hertz peak, but 9 and 11 hertz as well. So it's just to say that these low frequency modulations show up in the lower end of the spectrum. I don't know if that addresses what you mentioned.
Kind of. What I'm saying is that instead of doing this representation in the doing this asymmetric representation of the signal, you can just look at the continuous trace of the envelope of the signal, and that should supposedly give you the same representation as asymmetric representation.
I think that would be correct, because the envelope is an expression of the magnitude of the signal, and the mean of the signal is then modulated by, or it's dependent on the magnitude. Yeah.
Connected to that asymmetry index, I don't know about MEG, but in EG sometimes, how does this depend on the reference electrode actually that you choose?
Yeah, so that can make the amplitude asymmetry flip around from being positive to negative.
But it doesn't let it go away, or so it will always stay the same in magnitude and just flip in sign. But it doesn't depend on that, on the reference electrode, or the way you choose the reference signal?
I would say it's mainly depends on the sign. So if you move your reference electrodes, then your magnitude of the signal changes as well, then of course the amplitude asymmetry magnitude also shift, right? But basically it's a sign issue. And I didn't have time to get into this, but if you look at the back of the head, so, and I don't have the slide either, but nevertheless, if you look with MEG, right, what you see is that there's something positive or something negative. And that we actually explain by having one source setting here oscillating, and then on the right side producing peaks being modulated, on the left side producing troughs. And that is exactly what up to where the dipole is pointing, that you have the peaks modulated, and in the other end you will have the troughs. Yeah. So basically the flip in asymmetry should be consistent with the dipolar field patterns. And our Neuroscience paper was actually all about showing exactly that in order to substantiate our case. Yeah.
Do you see this as off control of these different networks, that it's very targeted toward different nodes, or it's we have a broad region that alpha goes up,
Yeah. Yeah.
by gamma?
Yeah. So that is then also related to the question you brought up about what about the ventral stream and alpha, right? So what one could criticize about this whole framework here is that we typically see alpha in parietal occipital regions and in sensory motor regions with MEG and EEG. So how general is this phenomenon, right? But there I think that EEG and MEG are actually somewhat crude measures, and we only get the peak of the iceberg. So if you look at data from intracranial recordings, you might see a much more widespread alpha. And now I probably should be a bit careful with how I phrase this, but and on many intracranial recordings, you do see activity in the theta and alpha band. And in patients with epilepsy, there might be a slowing of the frequency, so alpha actually goes down to theta. So some of the studies reported, for instance, by Mike Gahana on working memory modulations in the theta band, that could actually be alpha activity. So in order to really look into this, we need task specificity, right? We need to be certain that we turn on and off a given region, and then we have to look at this theta alpha-ish effect. And that would then allow us to explain how general these phenomena is. But just to make a long story short, I think we only see the peak, the top of the iceberg with EEG and MEG. Certainly, it's a given that if you look at intracranial data, you see a lot of theta alpha widespread over the whole brain, and we need to look into that with these glasses on.
Just a quick follow-up to that. Do you have any ideas on why alpha would be good for like preventing processing from happening? When you talk about
Yeah.
up the gamma and stuff like that, it seems like beta and gamma are both involved in after processing, but you have this band in the middle. Like why would it be shutting down?
Yeah. So what's special about alpha from a physiological point of view? Yeah. So then I would like to turn that around to the modeling crowd. Because that's exactly a question we can answer by having a good model of, say, alpha. So far, there is a fairly good model by Nancy Gopal based on post-inhibitory rebound. So you have excitatory neurons kicking off inhibitory neurons that then produce an inhibition to the excitatory neurons through calcium T. They make a post-inhibitory rebound, so you have excitation again, and that produce 100 milliseconds periods, right? But what you also get is a period with GABAergic inhibition. So one could then argue it is that GABAergic inhibition killing some of the activity in, between the spiking of the excitatory neurons. So Nancy Gopal has a fairly good model of that, but the problem about that model is that there's not a terrible lot of data to substantiate it, and we need that from the electrophysiologists.
Mm-hmm.